My name is Sidra. I'm a senior electrical engineering student, and I'm the captain of the Cal State LA RoboSub team.
Hi, my name is Joseph. I'm a senior mechanical engineering student, and I'm the co-captain and mechanical engineering lead for Cal State LA's RoboSub team.
Hello, my name is Kevin. I am a senior student studying mechanical engineering at California State University, Los Angeles. My role in the team is to design and build a frame for the sub.
I'm Ricardo Medina, a junior here at Cal State LA, majoring in computer science, and I was part of Donphan's CS team.
Hi, my name is Aren Petrossian. I'm a first-year mechanical engineering student, and I'm a member of the state machine team and the controls team.
My name is Eric Anthony. I'm a junior mechanical engineering student, and I'm the leader of the frame and hull team.
My name is Roberto Gonzalez. I'm a junior computer science student. I'm the lead of the computer vision team. Thanks.
My name is Saul Loza. I am a junior mechanical engineering student, and I am part of both the frame and hull team and the control systems team.
Our team is broken up into two sub-teams, each of which worked on the development of a separate vehicle. The first of these teams is our senior design team, which worked on the development of the vehicle that we've named Lantern. The senior design team consisted of 12 members, 6 computer science students, 3 electrical engineering students, and 3 mechanical engineering students. The senior design team is a collection of seniors who have participated in the RoboSub project in prior years and is overseen directly by our engineering advisors. The second of the sub-teams is our student organization, which is a team of lower-classmen looking for hands-on engineering experience through the development of an AUV. Their AUV was affectionately named Donphan. This team consists of around 30 members, whether those members joined the student organization to build the robot or simply to take part in our learning activities. Our advisors are Dr. Hei Shen and Dr. Mark Tefunction. Now let's hear from our team members about the development of our submarines, Lantern, and Donphan.
Lantern's hull is a box-shaped, waterproof electronics enclosure made of welded aluminum 6061 sheets. Key features of the hull are its gasket-sealed, removable lid, its forward and downward-facing camera enclosures, its connector bulkhead that interfaces the internal electronics with the external electronics exposed to the water, and its internal shelving unit that's connectorized and can be entirely removed from the hull for ease of maintenance. Manufacturability and maintenance were the two primary drivers in Lantern's hull design.
This year, the team opted to a modular design for both the frame and hull. The goal was to greatly improve the accessibility of all components on the sub in order to minimize the time spent on maintenance. The frame must be able to provide mounting surfaces for sensors, thrusters, ballast, and various mechanical devices. This is achieved by standardizing the way of how all components will be mounted onto the sub. The frame uses a custom T-slotted fixed rail design for the components to be quickly slotted in, then simply locked into place by a single bolt or set screw. Another improvement over previous generations of subs built at Cal State LA is optimal component placement. In the past, to get access to a specific component required the removal of other components in a way, which can take up to a whole day to disassemble and put those components back into place. The new system aims to provide better mounting solutions by placing the components that are likely to be swapped out at more accessible surfaces, and each mounting surface will be independent to one another, eliminating the need to remove other components in order to get access to another one.
Prior to Cal State LA's transition to online classes and remote work in response to the COVID-19 pandemic, the mechanical team had made solid progress in manufacturing Lantern's mechanical systems. 90% of our machining and water jetting had been completed, and we are preparing for welding, assembly, and integration. Since the transition to remote work, the mechanical team has conducted static and fatigue analysis to ensure our designs were robust enough to withstand expected loading conditions with a reasonable factor of safety and that they would last for years to come. We conducted stress analysis on our latch points, weld joints, vehicle legs, and our lifting lugs.
Lantern's electrical system consists of a motherboard, sensors, microcontrollers, and a power distribution board. The sensors include a barometer, an IMU, a DVL, a sonar module, cameras, and hydrophones. Each sensor provides the motherboard with information about the vehicle's environment, which can be used to interact with its surroundings accordingly. Some of these sensors require microcontrollers for data processing before the data is sent to the motherboard to avoid using resources that are reserved for image processing and decision making. The motherboard contains the state machine that outputs movement commands for the motors. This year, the electrical engineers on the Singer design team focused on the development of a smaller power distribution board, an active tracking system using the Blue Robotics ping sonar sensor, and the development of an acoustic localization system using hydrophones.
Hello, my name is Viraj Bhakta, and I am part of the computer science team for Cal State LA RoboSub. The computer science team is divided up into two sections, the computer vision team and the mission planning team. The computer vision team's goal is to use images from the camera feed for object detection and image recognition. The technologies they used were YOLO, You Only Look Once, Darknet, and OpenCV. The mission planning team's goal was to create a state machine to program the submarine's behavior. The technologies they used were ROS, Robot Operating System, and SMAC, State Machine. This is an example of a state machine made by the mission planning team. Now, although we were not able to implement our software and integrate it to the submarine and use live data, we were able to use test data and randomized data to test our software. So the state machine ran the scan gate state 3 times and the find gate state 2 times before it was able to select its role as the G-man and pass through the gate. We used OpenCV in our team for image preprocessing. So we used OpenCV to filter images and recognize objects. We used YOLO because it's very fast and it performs well on the hardware that we have. It was used to detect objects and to identify obstacles that we need to interact with. As you can see here, there are 2 pictures of the bootlegger symbol and the money symbol. And you can see that the computer vision system identified them both accurately as the bootlegger and the money symbol. Now, the conditions of the water were murky because we did not know what the competition scenario was going to be like. So we decided to go with slightly murky, opaque water. And this was identified by our computer vision system in real time.
The frame and hull team has had 2 primary design goals in mind from the beginning. We wanted to make it easy to access the internal components of the sub, and we wanted to make it as hydrodynamic as possible. To achieve these, the internal components can be accessed by just unthreading these 6 nuts that you can see around the top of the sub. And once you do that, the entire side can actually come off. You'll see some screws down at the bottom, but those aren't actually threaded all the way through. We filed off the threads at the end so that they act more as pins to hold the bottom plate in place. To improve the hydrodynamics, we made it so that the rounded section of the tube was in the direction of motion, as well as rounding off all of the edges of the other parts, such as the thruster mount that you can see here. And for the sections that we couldn't do that with, which you'll see such as the edge of the aluminum side plates themselves, we've instead minimized the surface area that would be perpendicular to the direction of motion.
This year, our team tried something new by using a Raspberry Pi as our motherboard with no other microcontrollers. The Pi was responsible for sensor data acquisition, running the controls code, computer vision, and doing the decision making. In the past, the team has used Arduino boards for sensor interfacing, but our success in this method has opened our eyes to other possibilities.
The controls for Donphan were straightforward implementation of PID systems for each axis of movement, responding to commands sent from the state machine. As for mission planning, Donphan relies on a simple state machine loop that searches for an objective, approaches the objective, executes the task, then disengages and records the completed task. Since we lack hydrophones, we are dependent on what we can see from computer vision, leading us to focus on completing tasks with a heavy visual element, such as a gate task. Each state related to the task is responsible for obtaining relevant data from the sensor modules, as well as controlling the submarine. Each approach and execution state is unique to the task, allowing the programming and testing of specific tasks without the need to have the entire state machine running. It also allows for setting a time limit on task, making the submarine move on and the task taking too much time. This modularity of the system will allow for greater reuse of code, as well as faster modifications without disturbing the function of other task states.
This year's computer visions team was tasked to develop a program to detect and classify objects within the course. In order to do this, the team decided to use OpenCV's built-in Cascade classifier. After successfully developing a classifier for objects within the course, the team's next step was to test. In order to test that our program worked, we inputted video into our program and had it put out two things: what it was looking at and where it was looking at relative to the camera.
Our strategy this year was to develop two different vehicles to complete different tasks during the competition. Lantern would be equipped with hydrophones and attempt the tasks marked by acoustic pingers. Meanwhile, Dawnfan would get style points from the gate and attempt the buoy tasks using its less sophisticated hardware. This strategy was devised in consideration of our limited budget and team organization. We reused several expensive sensors from previous years on Lantern to provide it with more capabilities, while Dawnfan was created with less expensive hardware and was intended to help our lower classmen learn about the project for future years. Our team also explored the possibility of inter-vehicle communication using computer vision, but we did not have the chance to test or incorporate this into our competition strategy.
While this year's team worked hard on programming and simulations outside of the lab, our members who will stay on the team next year have been working hard to organize workshops, presentations, and other ways of allowing members to participate in the RoboSub project remotely. Our advisors are even working on a full robotics course for students to take that will prepare them for RoboSub once students are allowed back in the lab. While we're sad our subs were left unfinished in the lab, we hope you'll get to see them swim in San Diego in the summer of 2021. Until next year,